All right, so we're still working on pipe flow, and now we're going to talk about what to do if your pipe isn't circular in cross-section. And what you do, it's pretty simple. You just use what's called the hydraulic diameter, or D sub H, in this equation. And here's our equation for our hydraulic diameter. And in this equation, the A is the area that you would use to calculate Q. That would be the cross-sectional area, so perpendicular to the flow wherever the fluid is. And then P is what's called your wetted perimeter, okay? And that is where the fluid is going to be in contact with a wall that is exerting shear on it, okay? So for instance, if you have a rectangular AC duct, and let's just say, for example, this is all just example, that this duct has width of 2A and a height of A. Okay, so the width is twice the length or the height. So our area, since this is all filled with air, so our cross-sectional area that we would use to calculate Q would just be the whole area. Height times width. So area, height times width would be 2A squared, right? And our perimeter then, so this air that's coming through this duct is in contact with all four walls here. So our perimeter is going to equal this wall plus this wall plus this wall plus this wall. Well, that's 2A plus 4A, 6A. Okay. So our hydraulic diameter then, DH, is equal to 4 times 2A squared over 6A. And this is just plugging into this equation above. All right, and if you simplify that a little bit, what we're going to get is 4/3 A squared, 4/3 A. All right, so that means that this is going to essentially act kind of like a pipe as far as frictional losses. It's going to act like a pipe with a diameter of 4/3 times that height A. So friction losses like pipe with this diameter, 4/3 times A. All right, let's do the same kind of thing with a drainage canal. All right, so this is a drainage canal, which means that you got a free surface here at the top. And let's say again, this is 2A wide and A high. Okay, so our cross-sectional area is still going to be A times 2A, 2A squared. And our perimeter this time is going to be a little bit different. So remember, the perimeter is only going to count if it's in contact with a solid wall, because the air interface here is just not going to exert very much shear. So we're going to just use our perimeter of A plus 2A plus A. A plus 2A plus A, 4A. Okay, so our hydraulic diameter for this case is 4 times 2A squared over 4A, which is just going to be 2A. Okay, so we ended up with a bigger hydraulic diameter for the drainage canal than we did for the AC duct, and that means that this is going to act like a bigger pipe, right? So for the canal, since what is negligible? Shear is negligible at the air interface. There is less area. So the walls, there are fewer walls that are exerting friction. Okay, so that the canal is going to act like a bigger pipe, because a bigger pipe has less friction than a smaller pipe. Okay, than the AC example. So we're going to have like a 2A diameter here. Okay, so that's how you calculate the hydraulic diameter. Now we're going to talk about how you use the hydraulic diameter. Basically, you just use it wherever you would normally use diameter, except for one caveat, except for when you're calculating that average velocity. So when it goes into the Q, or the flow rate, or if you're using flow rate to calculate average velocity, in that case you're going to use the real area, okay? But in your Reynolds number, in your frictional head losses, you are going to use this hydraulic diameter. So the Reynolds number for non-circular pipes is going to be rho VDH over mu, or VDH, hydraulic diameter, over nu. And we can say the same thing for HF. It's going to be FLV squared over 2DHG. Okay? And then the same thing again when we get to minor losses. If you had some minor losses, which we haven't gotten to yet, you would use DH in that. Okay. You can use the Moody chart or the equation to get F based on the round pipes with the hydraulic diameter instead. Also on the roughness, epsilon over DH instead of epsilon over D. Okay. So if it is the velocity, the average velocity, or Q that you're calculating, then you want to use the real cross-sectional area. So V here is Q over A. This A needs to be the real area. The same area you use when you calculated DH. Okay. Hydraulic diameter method, very much an approximation, like all of this stuff from experiments is an approximation. For turbulent flow, it's not too horrible. It's plus or minus 15%. But for laminar flow, it's actually really bad, plus or minus 40%, which is why a lot of these different areas are calculated for using the Navier-Stokes equation. And some have already been done for you, but you can, unless it's a really complicated geometry, you can go ahead and do the Navier-Stokes equations for laminar flow. Some of them have already been calculated for you. All right, so stop here and do quiz questions 1 and 2.